welcome back to Educare Foundation YouTube channel. If you are first time viewer of this channel, make sure you subscribe to our channel, like the video and share with your friends. So today we are going to look at estimation of infiltration. Now when it rains, we know that the water, the truth for that is the actual water that falls to the ground will infiltrate the soil, right? And we want to know the rate at which it occurs. When it rains and the soil is already saturated, the rate of infiltration will be low. When it rains and the soil is dry, the rate of infiltration will be high. If it rains over, let's say, a highly compacted soil, infiltration rate will be low because the water has to pass through the tiny pores. And if the soils are compacted, then it means that the pore spaces are reduced and so on. Now we have several tests that we use it. So we can have the modeling method that is using the Horton formula. So the Horton formula is used to model infiltration process. You can use the water budget method, water budget method to determine parameters of infiltration. We can use the sprinkling test. The sprinkling test is a lab experiment where we kind of replicate the whole process that happens when it rains. Then we have the infiltrometer test. That is what we are going to focus on. Though. So the infiltrometer test, where you have the double ring infiltrometer. So with the double ring infiltrometer, we have a very big ring. We drive it into the soil. Then we have an inner ring where we do our measurements. Then around the inner ring, we pour water. Then within the inner ring, we also pour water. Then we time ourselves. First of all, we measure the height of water level each knot and time ourselves by a certain interval, and we get to know the amount. Then, so this is what it was done to get these data, and out of that, we used to determine some parameters. Now, what parameters do we find? We find the initial infiltration rate, we find the equilibrium infiltration capacity, then we find the infiltration rate at any particular time, right? So these are the parameters that we use to infer what we want. So the initial infiltration rate, the equilibrium infiltration capacity, and infiltration at any point in time. So this occurs when the soil is saturated, right? This is the initial state. So we are going to look at this whole thing. Now with this test, with the infiltrometer test, that's what we said we are going to focus on. Based on the infiltrometer test, we are going to get a data that looks like this. A data that looks like this. So a data that looks like this. Then we plot a graph of the data. Then we get these parameters out of what? Out of what the graph. So let's start with it. All right, so let's look at this question. So the table below present observation made in a double ring infiltrometer test on KNUST campus, that's Kwame Nkrumah University of Science and Technology campus. In the test, a constant water level. So let me redraw the whole experiment structure. So this is how it looks like. Okay, let me take it from the side view. So the side view, it looks like this. Then we have the inner ring. So this is the outer ring, and this is the inner ring. This is the inner ring. Let me use a different color so that we can differentiate it. So we drive it into the soil, right, to make sure everything, there is no leakages at the side. Then we pour water. So let me use the blue color. So we pour water at the same time as we are pouring water into the outer deep chamber. We also pour water into this side. So the initial water level that we are going to start with is what? at this initial height at time t is equal to 0. So we always make sure that this water level is constant as we perform the experiment. You get it? Then we time ourselves. So when we started, the water level was 150. We time ourselves for 5 minutes. The water level dropped. So to find the drop in water level, we just need to find this height, and that will give us the this water level that we had. Then we topped immediately we finished taking the reading, we topped it up to the initial level. So at every point in time, the experiment began at the initial water level, which was for 150, and realized that the drop happened, the drop happened, the drop happened, the drop happened. At a certain point, we realized that there was a constant drop. Now we will infer what it means. So when you have this data, first of all, you need to continue how they call the table. So we have to continue the table. So let me continue the table in a bit. All right, so I've redrawn the table. So the first thing that we look at is the change in water head. Change in water head. Now the change in water head is the initial water level minus what? The new water level that we obtained. So at the beginning of the experiment, the initial water level is 150 and the at time equal to 0. So here will be dash. Here, so the initial water level minus the water level there will give us the change in water level. That's 150 minus 135, and that is what 15, right? Then 138 and 150 minus 138, that is what. So what you have to do is that this is the water level, HI, the water level at any time, any given time. So if you want to find a change in water level, is simply the initial water level, the water level at time equal to 0 minus the water level at that particular point. So if I want it, it's going to be 150 minus 138, and that is what 12. This one, 150 minus 140, that is what 10. 150 minus 135, that is 15. 150 minus 125, and that is what 25. 150 minus 13, so that is what 16. 150 minus 135, 15. 150 minus 137, that is 13. 150 minus 128, that is 22. 150 minus 128, 22, 22. Do you get it? Then we find the change in time. The change in time. So the change in time is Tn plus 1 minus Cn. So if I am here, if I am here, the initial is going to be dash. But if I am here, it's going to be what? My Tn plus 1 minus my Tn. So this is my Tn plus, sorry, it's supposed to be Tn where I am minus Tn minus 1. And that's how it's supposed to be. So this is my Tn minus my Tn minus 1. That is the previous time. So 5 minus 0 here is going to be 5, right? If I am here, it's going to be 10 minus 5, that would be what, 5. If I am here, it's going to be 15 minus 10, that is what, 5. If I am here, it's going to be 25 minus 50, that is what, 10. If I am here, 45 minus 25, that is 20. If I am here, 60 minus 45, that is what, 15. If I am here, 25 minus 60, that is also 15. If I am here, 90 minus 25, that is what, 50, I think. Then if I am here, 120 minus 90, that is, if I am here, 160 minus this, that one is 40. Here, this minus this, that one is 90. So with 40, let me check it. 120 minus 160. I think there is a problem with this question. This is supposed to be 150 at least. Wait, you let me. I think there is a mistake with the question. Here is supposed to be 150. 150, right? So here is supposed to be 150. So here is going to be what? It's going to be 30. 30, right? And here will also be what? 30. Now with that in place, we need to find our. Now this time is in minutes. You can turn it into hours, right? Now we can leave it like that. But we need to find filtration rate, which is given by a change in water level over what? A change in time. Now we want to leave our answer in um, millimeters. We want to leave our answer in millimeters per hour. So we have to change our time. So in that case, we have to multiply it by 60 minutes to make up for the time, right? Because we want to leave our answer, we want to leave our units in millimeters per hour, which is much more clearer, right? You can equally leave it in millimeters per minute, but the value that you are going to get are very, very small. And because we are going to plot it, so I'll prefer to leave it in millimeters per hour. So we just the change in water level, that is this, divided by this times what? Times your 60. So let's see what we do. Okay, so after finding the infiltration rate using the formula, that is the change in water level or the change in time. Because we want our unit to be in millimeters per hour, we multiply by 60 minutes because the time was in how do you call it? Minutes. So 60 um is going to be over minutes. Sorry, minutes over hour, 1 hour, right? Then we get this, right? Now after getting these things, what do? We plot them on a graph. So we plot them on a graph. So I have my graph here. Uh, excuse me. I have my graph here. So I just have to plot this on the graph, right? Okay, so let's see. Before I will label the graph, right? Now we plot the infiltration rate on this axis. So the infiltration rate on the y-axis, infiltration rate on the y-axis. Now we plot the infiltration rate against, so we plot the infiltration rate against time. So let me calm down a little bit and put my time here. My time here. So I'm going to put in this one. So the time ranges from 5, I'm sorry, yes. So it starts from 0, then ends with what? 180, right? So let's see how we do it. All right, so with the graph, so we are plotting the infiltration rate, which is the what we say, millimeters per hour. Then we are plotting against what? Time. I'm sorry. We are plotting against time, which is right time. We are plotting against time, which is in minutes, which is in minutes. So we take the time, then the infiltration rate. So this is what we will take. We'll come and take this 10, the infiltration rate, and the time that corresponds to the infiltration rate. And that is how we plot. So the first of all, let's see, let's start. So when time was 5, so let me zoom a little bit. I'm coming. All right, so we plot. So first of all, we look for 5 meters. That 5 minutes. So 5 minutes will be here on this first now because this the interval is 25. So each line is 5. So 5 to 180. So here 5 to 180. Then 10 to 144. So 10 will be the second line. 144. This 140 to here is 120, right? So this is 144. 140. The next line is 144. Anything. It's what? 10, right? Then we have 15. 15, the third line. And it's against 120. So 120. Then we come to 25 against 90, 25 against 90. So this 190 somewhere, 184, one sorry, 84, 88, then 96, 84, 88, 92, 96 here. So we have what? 90. So 84, 88, this 92. So it's going to be somewhere here, right? Somewhere here. Then we have 45. So 145. So this 25, um, 30, 35, 40, 45. So 45 is on this line. And it's against 75. So this 45 times 45. So 54, 68, 72, 76. So it's going to be somewhere here. The 75. Oh, what is it? The 75 is going to be somewhere here, right? Then times 60. So this 55, 60 times 50 give us a 64. So 64 is somewhere here. Then times 75 give us what? 60. So times 75, 60. Then times 90. So 75, 70, 80, 85, 90, right? That one give us 52. So 44, 44, 48, 52. So here 90, 52, right? Then 120. So this is 100, 105, 110, 115, 120 is here. And it's against what? 44. So this, okay, that's 44. And it continues. 150 is also 44. Then what? 180, which is here is also 44. Then we draw, how do you call it? A straight curve or a smooth curve across these points. So after drawing the smooth curve through, this is what we get. Then we extend this one backwards. We extend it backwards. Um, so we extend this backwards, touch this line. So where it touches the y-axis is your F naught, the initial. And where the curve flattens out, so it flattens out at this point. So we trace it, we trace that flattening part, that will be your what? Your FC. So our F naught, that is our initial infiltration capacity. We trace it here. So this 184, 88, 92, 196. So the F naught is equal to 196 millimeters per hour. This infiltration rate. And we had it in what? Millimeters per hour. And this is our time. We had it in what? Minutes. Then the FC, that is equilibrium infiltration capacity. That one, where the curve flattens out, you draw a straight line through it and you get it. So this is 44, 48, and that's what 48 millimeters per watt. So these are the parameters that we got. Thank you very much for watching. Make sure to like, subscribe, and comment, and share this video. Educate Foundation, because bye.